Hi, everybody. This is Physics 165, Climate Change Past and Present. This is a video lecture, Lecture 8. We're going to be talking about atmospheric structure and circulation. So we spent a lot of time talking about how energy moves through the atmosphere and heats up the planet and that sort of thing. So now we want to start talking about how the atmosphere is organized, how it moves, and what its sort of internal structure is. This is going to be really important because many of the effects of climate change deal with more than just the overall temperature of the planet. The distribution of temperature, the way heat moves around, changes in rainfall, changes in wind patterns, all of these are expected to change as a result of global warming. And it's only by understanding how the atmosphere is built and how it moves that we can really get to understand these. So I've got a bunch of questions in mind that I want to address in this particular lecture. Among these are, how do the pressure and temperature of the atmosphere change with height? So kind of what's the vertical structure? Also want to know how the atmosphere moves, and I'm focused particularly on the lower parts of the atmosphere, which is where we live. Um, we're going to focus on both north-south motions, up-down motions, and separately what causes the atmosphere to have winds blowing from east to west and west to east. And then the overall general question of what causes storms and where do those come from. Um, so a good place to start when thinking about the structure of the atmosphere is the fact that atmospheric pressure declines, gets smaller as you go up. You can see this if you go on top of a mountain and the air is really thin. But you can also get a really vivid look at this if you think about it's only a couple of hundred kilometers up before you get to like where the space station flies, and there's absolutely no air up there. Maybe you remember a few years ago, a wealthy daredevil named Felix Baumgartner took a helium balloon up to an altitude of 39 kilometers, that's like 20 some miles, um, and jumped out and parachuted down. He was in free fall for a good chunk of the way, may have broken the speed of sound on the way down. But you can see here at at a height of 39 kilometers, he's wearing basically a full spacesuit. There is some air still up there, but not very much, and certainly not enough to allow him to survive without the spacesuit. So let's try to understand why the pressure changes as you go from the bottom of the atmosphere up to the top. It's actually pretty simple when you realize that air has weight, and each successive parcel of air, as you go up in a vertical column, has to bear the weight of all the air above it. It's difficult to visualize air as an object. So just to kind of help with the illustration, let's imagine we have a bunch of sort of arbitrary sized blobs of air that are in like Ziploc bags. They're sealed bags so no air can get in or out. And we start stacking them. We lay one down, we lay the next one on top of it, next one on top of that. Now, since air weighs something, the weight of all these bags is going to be pressing down on the bottommost of the baggies. And that means that that bag is going to get super compressed. The next bag up doesn't have to bear quite as much weight, and so it won't be compressed quite as much, and so on all the way up to the top when you have a bag that really doesn't have to support any weight at all, and so it will be quite big and expanded. So the point is that the weight of all the overlying air parcels compresses the air. And so the air at the bottom, where there's the most weight above, feels the most pressure. So that is pretty simple to understand, I think. And of course, the plastic bag part of things doesn't actually matter. It's really just air sitting on top of air and so on. When you go ahead and do the math and calculate the pressure change with height, using basic physics techniques, you get the following sort of distribution of pressure with height. 1 bar is our word for the standard pressure at the ground. So 1,000 millibars is 1 bar, which is ground pressure. So in this graph, the vertical axis is height and the horizontal axis shows pressure. And so down at the ground, we have 1,000 millibars. As you go up from there, we get gradually less pressure and less pressure, and it declines exponentially as we go up. When you get to about 5 kilometers altitude, you're above about half of all the atmospheric mass, and the pressure is declined by about a factor of 2. As you continue on up for there, the height that airplanes fly, about 12 kilometers, the pressure is only a third of what it is at ground level, and so on. The pressure never really goes to completely to zero. It just declines exponentially and gets super, super, super small. And Felix Baumgartner was jumping from up here. Pressure declines with altitude in a kind of absolutely an exponential fashion. All right. You can, take measurements of this, of pressure and temperature as you go up in the atmosphere. One of the most common ways that we do this is with a device called a radiosonde. That's a complicated name for a weather balloon. And so here you see a weather balloon being deployed, and it has a string and it has an instrument package on the bottom of it. It ascends up through the atmosphere, collecting data on pressure, temperature, and a whole bunch of other variables as it goes up. We'll talk more about weather balloons and how they work later on in the class, because a lot of our important climate data comes from weather balloons. All right, so understanding that the pressure decreases as we go up, the next thing we want to talk about is temperature, and thinking about the change in temperature with height. Now, in order to understand that, we need a piece of basic physics first. We've got a tennis player here to illustrate this. And the basic idea is that if you have a fast-moving object, in this case a tennis ball, and it strikes another object and bounces off of it, all right, you can change the speed of the tennis ball by using this tennis racket. And so you have the ball coming in at a certain speed, it bounces off and it hits, and it leaves going back faster than it was going initially. The speed of the tennis racket contributes to increase the speed of the ball as a result of the collision. It's the same as a baseball bat, any number of sporting tools work the same way. Also, it's worth pointing that you can make it work the other way. So take, for example, a bunt in baseball. There, as the ball is coming towards you, you put the... I think I can do this. No, okay, all right. You put the bat in front of the ball, and as the ball arrives, you let the bat sink back a little bit, all right? And that subtracts from the speed of the ball, and so the ball doesn't fly off for a home run, but instead drops down at your feet. So depending on whether your moving object is colliding with a racket or a bat that's moving towards it or away from it, you can add to or subtract from its speed. All right, so the other important idea for understanding how temperature comes from is to remember what air is made out of. It's made out of molecules that are moving at high speed, bouncing around, within just colliding off of each other. If it's in a container, they'll be bouncing off the inside walls of the container. They're moving around at random and really at quite fast velocities. They behave a little bit like the tennis balls in the previous slide. Now, if we have a container full of gas and we compress it, all right, then we're taking the walls and we're moving them towards the little molecular balls as they bounce off the walls. It's exactly like the tennis racket moving towards the tennis ball. As a result of this collision, the molecules will bounce off the walls faster than they came in, all right? And so as we are compressing a gas, we will make the molecules move faster as a result of gaining energy through the collisions with the incoming walls. All right. And by the way, that works whether you have walls or not. Even if gas and air just compresses itself, the molecules moving closer together will have exactly the same effect. So the molecules move faster. So what? Well, remember from the very beginning of the class when we said we talked about what temperature is. Temperature is the random motion of gas molecules. And the faster they're going, the hotter the temperature. And so, as we compress the gas, we make the molecules move faster, and so the gas heats up. It's just that simple. All right. And so, if we compress a gas, it will heat up. If we reduce the pressure of a gas, it will cool down. So let's imagine taking a clump of air that starts at the ground and lifting it up to the top of a mountain. As it goes up, the pressure goes down. As the pressure goes down, the temperature goes down. And this is why you have the rather surprising result that it's cold on top of a mountain and it's warm on the ground. That's because the air is cooling off as a result of expanding as it moves from the ground up to the top of the mountain, and heating up as it comes back down. The net result of this is that we have a temperature profile in the lower atmosphere that decreases with height. Okay, so on the right-hand side of this graph, I've got the same pressure graph that I showed you earlier. Pressure reduces as you go up however many kilometers. And in exactly the same way, because the pressure is reducing, the temperature decreases. Down at the ground, it might be 300 Kelvin. That works out to about 90 degrees or something on a hot summer day. And as we go up, the temperature goes down dramatically until, at this point, roughly at the height that airplanes fly, 12 kilometers, the temperature is down to 220 Kelvin. That would be 50 degrees C below zero. That's probably 70 or 80 degrees below 0 Fahrenheit, which is something to think about as I'm flying to Japan, but just how cold the air is outside. That trend continues as you go higher up into the atmosphere through the region that we call the troposphere. It's called the troposphere. Tropos is Greek for turning, and this is the part of the atmosphere where the atmosphere is rising and sinking and overturning. All right, we'll talk more about that process, which is called convection, in just a minute. All right, but eventually we reach the top of that layer of the atmosphere, and at that point the temperature stops cooling and begins to warm. All right, and from here on, in a region called the stratosphere, the temperature actually increases as you go up. All right. Well, how can that be happening? Well, it can't be happening because of the molecular collision process that I talked about. There must be some outside force that's adding heat to the atmosphere in this upper region. All right. I'll explain that in just a second, but the overall trend is cooling as you go up in the lowermost 15 kilometers, and then heating as you go up beyond that height. And then once you get above 50 kilometers, it starts cooling again and then heating again. There's a whole bunch of layers above 50 kilometers, but for the purposes of climate change, we only have to worry about these two. All right, so why is the stratosphere warmer than the top of the troposphere? Well, it turns out it's all down to the ozone layer. All right, as you probably know, there's a layer of ozone, which is oxygen with 3 oxygen atoms bonded together. And this chemical is able to absorb ultraviolet light. That's what prevents us all from dying of skin cancer, and it absorbs the ultraviolet from the sun so that we stay safe. And there's been concerns about the ozone layer being depleted from human chemicals, but all that is aside from the point right now. It's still in good shape to absorb the ultraviolet light. But where does the energy for that ultraviolet light go? Well, it has to go somewhere, and in fact, it goes into heating up the air. The ultraviolet is absorbed by ozone. Ozone gains energy as a result and heats up. And so the reason the stratosphere has that increasing temperature profile is we're getting more and more absorption from ultraviolet light, and so it gets warmer and warmer as we go up. Right? Once you get above 50 kilometers, though, there's no more, really not much more ozone left, and so you don't get this effect anymore. All right, so we'll talk more about the stratosphere later on because there's some really interesting interactions between the temperature change in the lower atmosphere and temperature changes in the upper atmosphere that have to do with proving that greenhouse gases are the causes of the warming we see rather than any other effect. So we'll get back to that later. What I want to talk about now is convection. I said it earlier that the lowermost part of the atmosphere is constantly overturning. All right, let's think about why that happens. The sunlight strikes the ground and heats the ground. Therefore, the air in contact with the ground gets warm and begins rising up. All right, it's so warm air rises. Meanwhile, the air up higher in the atmosphere has cooled off, and so it begins to sink. All right, warm air rises, cold air sinks. All right, and as a result, the atmosphere begins to overturn, and we get this constant sort of flipping over kind of pattern. It happens on all scales from a few kilometers across to the whole planet. And let's think about the sort of implications for that. This process is called convection, all right? You've heard of convection oven? Well, that's what it does. So here we have warm air rising, all right, as a result of being heated at the ground, rising up. When you see those big clouds in the summertime, the big puffy thunderstorms, that is a tower of warm rising air. Once it gets up to high altitude, it begins to sink, all right? And the sinking air is usually transparent and free of any clouds. It's very dry, whereas all the rain is confined within the rising section. Now, why is that? Why do we get rainfall and clouds where the air is lifting and cool, dry, non-rainy air in the places where the air is sinking? Well, remember I told you about the Clausius-Clapeyron equation that relates the maximum amount of water vapor you can have in the air to the temperature. Well, that comes into play here. All right, let's imagine that we've got a warm parcel of air in contact with the ground, and it begins to rise. It has some humidity to it because it's been in contact with plants and water and, on the surface, and it begins to rise. All right. We said there's this maximum upper limit of water vapor that you can have. All right. From there, the air begins to rise, and as it rises, it cools. We talked about that just a moment ago. So as the air cools, it moves to the left on this diagram, and almost inevitably it'll eventually come into contact with this maximum upper limit of water vapor. It keeps its water vapor up until it hits this point, and at this point it's not allowed to go into here. This is beyond the upper limit of water vapor at that particular temperature. It has to convert that water vapor into liquid water, and so as it does, clouds begin to form. All right, that removes the vapor from the air and replaces it with liquid, which doesn't count on this diagram. And so now we continue to cool, going to the left as we go higher up into the atmosphere. And as we cool, we squeeze more of the water vapor out and replace it with liquid. And so we start getting puffy clouds. If this process happens enough and the little droplets get big enough, they turn into rain and they fall out of the atmosphere. So eventually we get up to the top of the cloud, and at this point there's very little vapor left, and the air begins to sink again, returning in that convective overturn. As it sinks, it gains temperature and it heats back up again. All right, but now there's no water vapor limit it has to worry about, and so it ends up much drier than when it began. Okay. All right. I think I mentioned in class that watching these videos can be, a little bit of a strain. Just sitting here listening to me talk in your dorm room or wherever you're watching this. So I'm going to take a short break and pause the video for a second and get back to this, and you might want to do the same. But we'll be back in just a minute to talk about how the atmosphere moves.